Now we can start talking about statistics. In the big picture, statistics is a rather broad subject, but we only have to know a few things for the test. For the purposes of the test, statistics consists of tools for making sense of data. So we'll get some data and we'll just be asked about this data. So, one of the most fundamental questions we can ask about a data set is, what single number is most representative of the set as a whole? And this turns out to be very important in real-world statistics. For example, if we had a list of the household income of everyone in the United States, we'd want to know what's one single number that would be representative, most representative of that entire list. Well, such numbers are called measures of center. And that's what we're going to start talking about in this video. The two most important measures of center are mean and the median. A mean is simply an ordinary average. To find the mean, say, of 7 numbers on a list, you would add up the 7 numbers and then divide this sum by 7. In general, on a list with n entries, we add up all the entries and then divide by n. That's the mean, just an ordinary average. We can write the formula as mean equals the sum of n entries divided by n. That's the formula for the mean. Notice that this formula is also quite useful in the following form. If we just multiply both sides by n, we get n times the mean. In other words, the number of people on the list times the mean has to equal the sum of the entries. Thinking about sums is often the key to many questions about average or mean. So this second form, it's really underappreciated how powerful this form is. For example, here's a practice question. Pause the video and then we'll talk about this. Okay, in a class, 18 students took a test and had an average of 70. Alicia and Bert then took the test and the average of all 20 students was 71. If Alicia got a 77, then what was Bert's grade? All right, so a lot of people would find this a very hard question. The key to this question is simply thinking about the sums. So first of all, the old sum, those 18 people, I'm just going to take 18 times the mean of 70, multiply that out, and that's 1260. Well, now the new sum of all 20 students, that's going to be 20 times 71, multiply that out, that's 1420. Well, think about that. The old sum and the new sum, what's the difference between them? The only difference is we added Alicia's score and Bert's score to the other 18 scores. So the difference between them should be the sum of the score of Alicia and the score of Bert. So we subtract them, that sum. So Alicia's score and Bert's score must add up to 160. Well, if we subtract Alicia's score of 77, then we get 83, and of course that has to be Bert's grade. So that's how we answer that question, purely thinking about sums. Now the median. The median is the middle number on a list. We have to be a little careful here. We have to put the list in ascending order first, that is, from smallest to biggest. Technically, the median is the middle number on an ordered list. So we can't just write them in any jumbled order and then say, okay, the median is the one that happens to be sitting in the middle of that jumble. No, we have to put the list in order from smallest to biggest. And often, incidentally, the test will not do that. They'll give you the numbers in a jumbled order, and then you yourself have to put them in order and then find the median. So you have to be careful with that. So if we have this list, for example, the number right smack dab in the middle is 4. So that's the median. There are 3 numbers below it, 3 numbers above it, clearly in the middle. Now this list is a little bit interesting because there's an even number of terms on the list, not an odd number, so there's no one number at the middle. At the middle we have these 2 numbers, 4 and 5, and they can't both be the median. So what we do if there's an even number on a list, we average the 2 middle numbers. And so the median is between 4 and 5. We take the average of 4 and 5, which is 4.5. That is the median. Suppose we're given this list. Well, the very first thing we have to do is put that list in order. So now it's in order. So now the median, there are 1, 2, 3, 4, 5, 6, 7, 8 numbers on this list. And so the median has to be between 8 and 13. So we're going to average 8 and 13. 8 plus 13 divided by 2. 21 divided by 2. 10.5. 10.5 is the median of list K. Notice that the median only takes into account the number or numbers at the very center. We could change the numbers at either end of the list, and this change wouldn't affect the median at all. So for example, in that particular list, suppose we changed the 55 to 55,000. The median wouldn't change at all. The mean would change, but not the median. We'll talk about that in the next video. Here's a practice problem. Pause the video and then we'll talk about this. Okay, the median of list B is exactly 4 higher than the median of list A. All right, so the very first thing we need to do is find the median of list A. We put the terms in order. The median is the average of 7 and 10, which is 8.5. That's the median of list A. The median of list B has to be 4 higher than this. So it has to be 12.5. That's 8.5 plus 4. All right, so now let's think about this. There are 3 numbers that are less than that median. 4, 7, and 10 are all less than the median. 18, 25, and X must be greater than the median. And in fact, that 12.5 must be the average of 10 and X. So 12.5 is the average of 10 and X. We'll multiply by 2. What we get is 12.5 times 2 is 25. Subtract 10. We get X equals 15. And so that's the value of X. If X has a value of 15, then set B would have a median of 12.5, which is exactly 4 higher than 8.5. One final measure of center is the mode. You often hear these 3 said together, mean, median, and mode. What's the mode? The mode is the most frequently appearing number on the list, the number that makes the greatest number of appearances. This is far less important than either the mean or the median, for a variety of reasons. Some lists have a single mode. So for example, there are a lot of 3s on this list. There are 3 3s, and every other number only appears once. So the mode is clearly 3. Some lists have 2 modes. For example, in this list, we have a pair of 2s and also a pair of 5s. So the modes are 2 and 5. If all the numbers on the list are different from one another, as is usually the case, then there simply is no mode. So sometimes there is a mode, sometimes there's more than one, and often there's just no mode at all. So think about this. Every single list on the planet has a mean. Every single list on the planet has a median. But only some lists have modes. Some may have more than one mode, and many have no mode at all. And so this is one of the big reasons why the mode is not nearly as important as the mean or the median. In summary, the mean is the simple average. Often in questions about mean, it's helpful to think in terms of the sums. So the sum of the entry equals the number of entries times the mean. We just rewrite that formula at the top to get this. The median is the middle number of an ordered list. If 2 numbers are in the middle, then we simply average those numbers. And the mode, the most frequently appearing number, is just less important. Some lists have a mode, some have more than one, and many have no mode at all. Theoretically, the test could ask you about a mode, but it's much, much less common than questions about mean or median. More on mean and median. In the last video, we noted that changing the highest or lowest number in a list would not change the median, but it would change the mean. Numbers far away from the center of the list are called outliers. The mean is heavily influenced by outliers, and the median is entirely unaffected by outliers. And this is important. First of all, when are the mean and the median the same? Well, if the list consists of evenly spaced numbers, then the mean equals the median. Consecutive integers and consecutive multiples of the same number are examples of evenly spaced lists. So for example, we take this list, the mean and the median of both lists is 11. Also, mean and median are equal whenever the list is entirely symmetrical. What do I mean by that? Well, consider this list. Of course, the median is the middle number, 25. Now think about the other numbers. 23 and 27 are both exactly 2 away from 25. 13 and 37 are 12 away from 25. 8 and 42 are 17 away from 25. And 4 and 46 are 21 away. Another way to see that, incidentally, is that 13 plus 37 is 50, 8 plus 42 is 50, and 4 plus 46 is 50, all of which are double of 25. And so that means that everything is symmetrical, perfectly symmetrical around 25. If we put these as dots on the number line, it would be a completely symmetrical pattern of dots. And so because the entire list is symmetrical around 25, it means that the mean equals the median. Both are 25. When the list is asymmetrical, then the mean and the median differ. In particular, when there's a distinct outlier or set of outliers in one direction, those outliers pull the mean away from the median. So it's as if the median sits still and the mean gets pulled away from it. And so here we have a symmetrical list. Mean equals median equals 4. Now if we take that last number and make it much, much higher, well, the median is still exactly the same, but now the mean is going to be much, much higher than 4. If a test question asks you to compare the mean to the median, you don't necessarily have to calculate the mean. This is very important. Often it's enough to notice in which direction the most pronounced outliers lie. The mean follows the outliers. High-value outliers cause the mean to be higher than the median. So here's a practice question. Pause the video and then we'll talk about this. Okay. On a test in a class of more than 40 students, the scores had mean equal median equal mode equal 81. 2 absent students then took the test, so 42 took it all together. And these 2 students got grades of 83 and 47. What are the new mean and median? Well, first of all, notice that those 2 grades are both symmetrical around the median. So we have lots of numbers at 81. The median is 81. If we add something higher than 81 and something lower than 81, the median is still going to be 81. So the median is not going to change. So we can eliminate C and D right away. So the median is still 81. What about the mean? Well, notice that before those 2 students took the test, the mean and the median were both 81. Well, now we added one grade that was just 2 above the mean, but then we added a grade that was significantly lower than the mean. So that 47 is an outlier, and that's going to pull the mean down, pull it below the median, and so the mean is not going to stay the same, and in fact, we're going to have a lower mean while the median stays the same. Answer choice B. In summary, if all the numbers on a list are evenly spaced, or if the list is symmetrically distributed, then the mean equals the median. Outliers pull the mean away from the median, and we can often compare mean and median, or infer which one got bigger or smaller, without doing a calculation, purely by observing the direction of the outliers. Now we can talk about weighted averages. Sometimes the test will ask us for the combined average of 2 or more different groups. Here's a sample problem. We're not going to solve this yet, but just to give you an idea of what this situation is like, we'll look at this problem. On a ferry, there are 50 cars and 10 trucks. The cars have an average mass of 1,200 kilograms, and the trucks have an average mass of 3,000 kilograms. What is the average mass for all the vehicles on the ferry? And so we have 2 different groups. We have an average for each group, and we want to come up with the average for everything put together. There are a few different ways to approach a problem such as this. The first approach would be to think in terms of sums. As we discussed in the first lesson of this module, thinking in terms of sums
can often simplify problems about averages. And it's very important to remember, we can't add averages, we usually can't average averages, but we can add sums. And if we know the sum of one group and the sum of the other group, all we have to do is add them and we'll get the sum of the whole group. And so thinking about sums is often the key to working through average problems, and that includes weighted average problems. In that problem with vehicles, we have the actual number of each type of vehicles. Since all the masses are in 1,000, we do the calculations of everything divided by 1,000 just for simpler numbers. So here's the problem again. And so how would we find the sums? Well, sum is average times number. So for the cars, that's going to be 50, and I'm going to, instead of writing it as 1,200, I'm going to divide by 1,000 and just write it as 1.2, just so we don't have a bunch of extra zeros floating around. 50 times 1.2, that's the same as 5 times 12, which is 60. For the cars, for the trucks, we have 10 trucks, and then the mass, we'll just call that 3. 10 times 3, of course, is 30. Those are the two sums. We add up the sums. The total sum is 90. And we have a sum of 90, and we want the average over all 60 vehicles. Well, 90 divided by 60 is 3/2, or 1.5. And again, that is the mass divided by 1,000, so we just multiply by 1,000 again. 1,500 is the answer. 1,500 is the average mass of all 60 cars on the vehicles, on the ferry. And notice, incidentally, first of all, that average is between these two numbers. It would have to be between those two numbers. And in fact, it's a little closer to cars because there are more cars. So that kind of makes sense. If you find the average of two groups and the number you get is not between them, then you probably have done something wrong. The weighted average always has to be between the average of the two groups, or somewhere in the middle if it's three or more groups. So using sums is one way to approach weighted average problems. Another approach, a very different approach, involves thinking about proportions. In some problems, each group of individuals is some proportion or percent of the whole. And so in the problem about cars on a ferry, we actually gave you counts. We said, this is the number of cars, this is the number of trucks. Instead, it might be that the groups are broken down by percentage. This is the percent of group 1, this is the percent of group 2, percent or proportion. We can simply multiply the average of each group by this proportion, find the sum of these, and that sum is the average of the entire set. So just algebraic, let's talk about this first. Suppose there are 3 groups, and they each have averages, A1, A2, A3. Those are the averages of our 3 groups, or our 3 categories. The first group is P1 of the whole. That's its proportion. The second is P2, the third is P3. In other words, if they're given as percents, we would just change the percents to decimals. Then we'd have the proportions. And of course, all the proportions should add up to 1. All we have to do is take the product of each average times its own proportion. So average of the first group times the proportion of the first group, plus average of the second group times the proportion of the second group, plus, and do that for each group, and that sum will be the average of the whole. Here's a practice problem. Pause the video, try to do that on your own, and then we'll talk about this. Okay, so notice here, we don't know the actual number of people at the company. We don't care about the number of people at the company. All we're given are percents, which are very easy to change to proportions. 70%, 20%, 10%, 0.7, 0.2, 0.1. Those are the proportions at this company. And we have the average for each group. So again, all these numbers are in 1,000. We don't want to deal with the extra zeros, so we're just going to call these averages 40, 80, and 120, and leave off the extra zeros to save ourselves writing all those extra zeros. So all we're going to do for the average, we're going to multiply the proportion. So for the marketers, they're 0.7, multiply that by 40. The programmers, 0.2, multiply that by 80. And the managers, 0.1, multiply that by 120. Well, 0.7 times 40 is the same as 7 times 4, and 0.2 times 80 is the same as 2 times 8. So that's 28 plus 16 plus 12. Of course, 12 plus 28 is 40, plus 16 is 56. And again, this is divided by 1,000. We have to tack on the extra zeros to get the actual number. That actual number is 56,000, and that is the average salary of all employees at the company. So one way to find the weighted average is to find the sums. Find the sum of the first group, add the sum of the second group, add over all the groups if we have more than 2 groups, and then you'll get the total sum. You can just divide the total sum by the number of individuals. And if the problem gives it to you in proportions, all we have to do is multiply each average times the proportion. If it's a percent, we just have to remember change that percent to a decimal. A1 times P1 plus A2 times P2 plus etc. Add all those up, and that will be the average of the whole.
In the first weighted average video, we discussed 2 straightforward methods that can be used to solve these problems. So that first video, you could say that was kind of a lesson designed for everyone. Here's what you need to know to solve weighted average problems. And they're not really too bad if you understand these basic techniques. In this video, I'm going to show you an advanced technique. If you are good at math and a good visual thinker, this could be a time saver. You absolutely do not need to know this. And so what I'll say is, if math is a struggle to you, please do yourself a favor. Don't even watch this video. It will just confuse you. Don't worry about it. You don't need it at all. This is a video for people that are really good at math, and it can show you a time saver. And if you're curious, by all means, watch it. But keep in mind, don't be frustrated if this is something that is not natural to you, because it is something quite advanced. So just to summarize, in the first lesson, we talked about 2 basic methods. We can find the sum of each subsection and add the sums. This works if we have the actual counts of the sums. If rather than counts we have proportions or percents for every subsection, we can multiply each subsection's average by those same subsection proportions and add those. And so we saw this formula in the first video. So again, those are the very straightforward methods. We can use another kind of proportional reasoning if the weighted average involves only 2 groups. Suppose the 2 groups have proportions P1 and P2, so those are 2 proportions that add to 1, and we're going to say for the sake of argument that P1 is the bigger group. So P1, group 1 is bigger than group 2. If we think of the averages on a number line, the average of the whole collection will be somewhere between the average of group 1 and the average of group 2, and it will be closer to the average of group 1 because 1 is the bigger group. It would have to be closer to it. So it would look something like this. So again, group 1 is the bigger group, and so the average is going to be closer to it. In fact, the proportion of those distances on the number line will be the same as the proportions of the size of the 2 groups. Of course, the average of the bigger group will be closer to the total average, so the bigger group will have the smaller distance. So again, 1 is the bigger group, so it has D1, the smaller distance. But if we take the ratio of those distances and the ratio of the sizes of the groups, and of course we have to flip them over, big goes with small, small goes with big, that sort of thing, but we can set them equal, and it's the same ratio. Now, typically we don't set up that ratio, but we use that ratio to solve problems. So here's a problem. We had this in the first video. On a ferry, there are 50 cars and 10 trucks. The cars have an average mass of 1,200 kilograms. The trucks have an average mass of 3,000 kilograms. What is the average mass of all of them? So the weighted average of all 60 things altogether. Well, the proportion cars to trucks is 5 to 1 or 5. Another way to say this is cars are 5 parts, trucks are 1 part. And so altogether in all vehicles, that's 6 parts. So cars are 5/6 of all the vehicles and trucks are 1/6 of all the vehicles. And so the proportion between the between the two groups is 5 to 1. Well, that's going to have to be the same proportion on the number line. We have these two averages, 1,200 and 3,000. Think of them as their locations on the number line. And we're going to have a 5 to 1 ratio in the breakdown of the distances from the weighted average to those two individual averages. So let's think about that. That distance is 1,800. Well, just as the whole group of vehicles is divided into 6 parts, we have to divide that into 6 parts also. So how do we divide 1,800 into 6 parts? Well, we divide it by 6. 1,800 divided by 6 is 300. So 300 is 1 part. And so that means the larger group, cars, are 1 part of the distance, or 300 away from the average. And trucks, which is the smaller group, they're 5 parts away. And so the easiest thing to do, just start from the cars, which are 1,200, and 1 part away from that is plus 300. So we move up 300. 1,200 plus 300 equals 1,500. We could also start from trucks, 3,000, move down 5 parts. Well, 5 times 300 is 1,500. 3,000 minus 1,500 is again 1,500. So this is the same answer we found the first time. Here's a harder practice problem. Pause the video and then I'll talk about it. So at Deviation Corporation, there are 2 classes of employees, silver and gold. We have that the average salary is $56,000. It's $56,000 higher than the average of the silver. So we have the difference between the gold and silver. Notice we don't actually have the actual number, what is the average salary of the gold employee. We don't have that number. We don't have the average number of the silver. All we have is the difference between them. Then we're told the size of the 2 groups. And we want to know the average salary for the company is how much higher than the average salary for the silver employees. Well, let's think about this. On a number line, somewhere there'd be an average for the silver. Somewhere higher, there would be an average for the gold. The difference between these is 56,000. And we'd expect the average for the company, of course, it would have to be between them. And because gold is a slightly bigger group, it would have to be slightly closer to the gold side. And so we're trying to ask for this distance, how much higher is that company average above the average for the silver employees? So let's think about the size of the groups first. Let's set up that ratio because we know those numbers. 120 to 160. 120 is 3 times 40. 160 is 4 times 40. Divide by 40. We get a ratio of 3 to 4. So silver employees are 3 parts, gold employees are 4 parts. There are 7 parts in total. So now let's think about distances on the number line. From the average of silver up to the average of the total is 4 parts of the distance. From the average of the total up to the average of the gold is 3 parts of the distance. And again, there are 7 parts in total. Well, we know that those 7 parts altogether make up a difference on the number line of 56,000. So 7 parts equals 56K. Divide both sides by 7. We get 1 part equals 8,000. Well, now we know how big a part is on the distances. Well, from the silver to the gold is 4 of those parts. Well, what is 4 times 8,000? That's 32,000. So the total average for the company is $32,000 higher than the average for silver. If there are only 2 groups, the distances from the 2 group averages to the total average are in a ratio that is the reciprocal of the ratio of the proportions of the sizes of the groups. If you intuitively understand this approach, it can be a time-saving trick on advanced weighted average problems.
So far, we have discussed measures of center, mean, median, and mode. These give us a rough idea where the middle of a list is or what the most typical members of the set are. Often we also want to know how far the numbers on the list are from each other, that is, how spread out they are. Now you may wonder, why is this important? Well, suppose we have this scenario. We have a town of 100 households and it has an average income of $100,000 per year. And we could ask the question, what kind of town is this? In general, are the people in this town rich or poor? What's going on in the town? What's the story of the town? We might ask, for example, how do those households in those towns compare to the median household income in the United States, which is $51,900? Well, scenario number one would be all 100 households have exactly $100,000 in annual income. And so that means that every single one is about double the median for the United States. So everyone in the town, this would be a town of great prosperity. This is a town where everyone is doing quite well. So that is one story. Here's a very different story. Scenario number two. 50 households have $40,000, which is below the median for the United States, and the other 50 have $160,000. So 50 of them are doing very well. And then the other 50 are really kind of struggling. So you get this split. About half the town is struggling and half the town is doing well. That's a very different story. Now consider this story. 99 households have exactly $5,000 in annual income. So that would be extreme poverty. 99 of the households in the town are living in abject poverty, and one household is making over $9 million a year. So this still would have the same average. But notice that this is a very, very different story from the stories we've had before. So, in other words, just knowing the measure of center and not knowing anything about the spread can drastically change the kind of town. So all three of these scenarios have the same average, but the spread between the numbers becomes greater and greater from 1 to 3. Spread is an important factor in understanding the story of any set of numbers. And in fact, in the larger picture, this is exactly what statistics is about. Statistics is trying to figure out the story of a set of numbers. What does this set of numbers actually mean? That's what statistics is trying to do, and this is an example of it. Just as we discussed measures of center, we will also discuss a couple measures of spread. Now, both of these terms, measure of center, measure of spread, these are not terms you need to know for the test. These are only terms we're using in this video just to categorize the ideas that we're discussing. The first measure of spread that we'll look at is the range. Range is by far the simplest and least sophisticated measure of spread. The range is simply the max minus the min. So in other words, we take the highest number minus the lowest number, that's the range. This measure of spread only tells us about the difference between the extreme highest value and the extreme lowest value. It doesn't tell us where most of the points are between. So consider this. Suppose we have a set of 10 with a mean of 25 and a range of 20. And we want to know, what kind of story do we have here? Well, story number one is we have most of the values are at the mean, and we just have a couple outliers. So that's one example. Another scenario is that everyone's an outlier. You just have 5 numbers at the extreme low end and 5 numbers at the extreme high end. And then we could also have something like this, where most of the values are close together, but there's one high outlier. And you could imagine differently, we could arrange it so most of the numbers are close together, but there's one low outlier. So there are a variety of different stories that we could have given the same mean and the same range. Range is quite easy to calculate, but the information it gives us is quite limited. Notice that the range takes into account only 2 values, the max and the min. A more sophisticated measure of spread would take into account every value, just as the mean takes into account every value. And this more sophisticated measure of spread is in fact the standard deviation. In order to discuss what standard deviation is, we need to discuss the idea of a deviation from the mean. If we take any list and subtract the mean from every number on the list, we get a new list, and this new list is the list of deviations from the mean. So for example, here's a very simple list. The mean is 5. Subtract 5 from every number on the list, and we get this new list. These are the deviations. So 1 has a deviation of -4 because it is 4 units below 5. 7 has a deviation of 2 because it is 2 above 5. Those are the deviations from the mean. Notice that numbers below the mean have a negative deviation, numbers above the mean have a positive deviation. Notice also, if we simply took a numerical average of the deviations, that average would always be 0. So what we'd like is a typical size of the deviations, but we can't simply average the deviation list because that always gives 0. Standard deviation is a way to measure the size of a typical deviation. In other words, we're asking the question, how far away from the mean are the individual points? The standard deviation is the best, it's a representative answer to that question. In fact, it's the best single answer we could give to that question. I'll talk a little more about that in later videos in this module. But the standard deviation is fundamentally answering that question, how far away from the mean are the individual data points? What's a typical distance from the mean? The actual technical calculation for standard deviation is a bit complicated and will be covered in the next lesson. Here are some important facts about standard deviation. And if you know these facts, these quick and dirty facts, you'll know almost everything you need to know about standard deviation for the test. Fact number 1, the standard deviation can only be positive or 0, never negative. It's a distance after all, and distance can be positive, it can be 0, but it can't be negative. Fact number 2, the only way standard deviation can equal 0 is if all the numbers on the list are identical to one another. So let's think about this. Suppose we had a list like this. All the numbers are equal, every entry equals 7, so of course the mean equals 7, and if we subtract 7 from every number on the list, we're just going to get a set of zeros. The set of deviations is just a list of zeros. So the standard deviation has to be 0. The typical deviation is 0, so the standard deviation equals 0. Fact number 3. This is a bit of a trickier one. If all the numbers on the list are exactly the same distance from the mean, that distance is the standard deviation. So this can be a little harder to see. But if we look at a list like this, here's the mean is 5. Notice that every number on that list is a distance of 3 away from the mean. 2 is 3 less than the mean, 8 is 3 more than the mean, but on the number line, every single number, if we measured the distance from that number to the mean, every single number would have the same distance. That distance is 3, so the standard deviation of this set has to be 3, because every single entry is a distance of 3 away from the mean. This is a rare fact that might be tested on the hardest quant problems. This is a more applicable fact. So this is not about a calculation, but just about comparing standard deviations. A set with most numbers clustered toward the extremes will have a higher standard deviation than a list with most values equal to or close to the mean. So for example, suppose we're looking at these two sets. Notice that set number 1, most of those numbers are at the mean. 8 of the 10 numbers are at the mean of the set, so most of them are clustered toward the center. Set B, everything's clustered toward the edges. You have a bunch of very low values and a bunch of very high values. Now for set B, we have a set where every number is a distance of 10 away from the standard deviation. So for set B, we can actually figure out the standard deviation. It has to be 10 because all the numbers are 10 away from the mean. Set A, we don't need to be able to calculate the standard deviation. In fact, most times when you have to compare standard deviations, it's not a matter of doing a calculation. Instead, we're just going to simply notice. B, most of the numbers are far away from the mean. A, most of the numbers are close to the mean. In fact, most of the numbers are equal to the mean. And so that's going to mean that is going to have a much lower standard deviation because most of those numbers are very close to the mean. In fact, if we thought in terms of a list of deviations, 8 of those 10 numbers have a deviation of 0. And so having a list with mostly zeros, that's going to bring down the value of the standard deviation. So we don't need to calculate what it is, but we certainly know it is less than 10. And again, when you're asked to compare standard deviation, rarely are you being asked to perform a calculation. Fact number 5. If we add the same number to every number on the list or subtract the same number from every number on the list, the standard deviation doesn't change. So we look at these 3 lists, 1, 2, 3, 4, 5, 6, we add 40 to every number on the list, or we start with A and we add 71 to every number on the list. In either case, in all 3 cases, we just have a set of 3 consecutive integers. So those always have the same spacing. In other words, the steps are 1, 1, 1, 1, 1. Those are the steps as we move across any of those 5 sets, any of those 3 sets. So these 3 sets, and in fact, any set of 6 consecutive integers, have exactly the same deviation. And again, calculating that deviation is not important. What's important is that you can compare these and see immediately that they have to have the same standard deviation. Similarly, let's start with this. Now, this is an asymmetrical set. Notice the steps between the numbers. From 2 to 3 is 1, from 3 to 5 is 2, from 5 to 8 is 3, from 8 to 13 is 5, and from 13 to 21 is 8. So the steps are 2, 3, 5, 8, and 13. Set E, all we've done is we've added we've added 30 to every number on the list. So the spacings are still exactly the same, so this has the same standard deviation. Now this one's a little bit trickier. It doesn't actually look the same, but notice that the steps are in the reverse order. That if we start at 78, then we're stepping down by 1, then 2, then 3, then 5, then 8. So we're taking the steps in the reverse order, but the same steps are still there. In fact, one way to think about set F, if we subtract each number on D from 80, so 80 minus 2, 80 minus 3, 80 minus 5, that produces the numbers in F. And all 3 of these have the same standard deviation. Standard deviation has only to do with the spacing between the numbers, not where they are on the number line. Imagine the numbers of a set as dots on a number line. We can slide that set of dots up and down and even reflect it. As long as the spacing between the dots stays the same, the standard deviation stays the same. Start with these dots. We slide them up. Notice these spacings stay the same. We even reflect it, but these spacings, now they go from right to left instead of left to right, but those spacings are still the same. That's what standard deviation is measuring, the spacing between the numbers. Where they are on the number line, or whether they go left to right or right to left, does not matter at all. Fact 6. If we multiply every number on a list by positive number k, the standard deviation also gets multiplied by k. So start out with this list here. It has a mean, and we'll just call it the standard deviation q. It doesn't matter what it is, the actual value. Now multiply everything on the list by 3. And notice what happened when we get multiplied by 3, the spacings get multiplied by 3. Between 3 and 5 is a spacing of 2, while between 9 and 15 is a spacing of 6, which is that spacing multiplied by 3. Between 7 and 11, we have a spacing of 4. Between 21 and 33, we have a spacing of 12. That spacing, again, has been multiplied by 3. Well, the new mean gets multiplied by 3, and also the new standard deviation gets multiplied by 3. So if you multiply every number on a list by a positive number k, both the mean and the standard deviation get multiplied by that number. Measures of spread tell us how far apart numbers on a list are from each other. The range is the max minus the min. If all the numbers on the list are identical, then the standard deviation is 0. If all the numbers on the list are the same distance from the mean, then the standard deviation equals that distance. Lots of points close to the mean give you a smaller standard deviation. Lots of points far away from the mean give you a larger standard deviation. If we add or subtract from every number on the list, that doesn't change the standard deviation at all. And if we multiply a list by some positive number k, then the standard deviation gets multiplied by that number. More on standard deviation. This lesson will cover 3 more advanced topics concerning standard deviation. So right away I'll say, if you're just worried about getting the basics of standard deviation, everything you learned in the last video, that will really help you with standard deviation. These are relatively specialized, rare questions, and you would only be seeing these if you were really doing very well in math and getting the hardest questions on the test. So I would not worry about this. If you're just worried about the basics of standard deviation, you could just skip this video. These are very advanced topics. Topic number 1 concerns how the standard deviation would change when we include new members to a list, making the list longer. This is a tricky issue for a few reasons. Let's say we have a set with 20 members, and the set has a mean of 50 and a standard deviation of 5. So what we have here are known as summary statistics. We know the overall mean, the overall standard deviation. We don't have the list of individual data. Suppose we're going to include 2 more numbers to bring the total number of members to 22. Suppose we include 80 and 80 as the 21st and 22nd members of the list. Of course, this would change the mean, and if we wanted to, we could calculate the new mean. The new mean would be slightly more than 50. But all the deviations change, so it is impossible to calculate the new standard deviation. So first of all, this is a subtle distinction. If we have the summary data, just the old mean, the old standard deviation, and then we add these 2 new points, we have absolutely no way to calculate the new standard deviation. Now, if we had the list, the original list of 20 values, and then we added the 21st and 22nd values, if we had all the values, then we could calculate the standard deviation. But even then, that's a calculation the test is not going to ask you to do. So in either way, you're not going to have to worry about this calculation. All we can say is that if we include new members that are far away from the mean of the set, the standard deviation of the new set will be larger. So that's very clear. The 2 values of 80 are way far away from all the other numbers. They're really big outliers. So adding really big outliers, that's going to increase the standard deviation. That you'd need to know. We can say a little bit more if we include a pair of numbers that doesn't change the mean. If we include numbers that are equally spaced around the mean, so one is k units above the mean, one is k units below the mean, then we will not change the mean. So the deviations from the mean for all the numbers on the list will stay the same, and we can draw some more detailed conclusions about what the standard deviation will do. Again, let's start out with that same set, 20 numbers, mean of 50, standard deviation of 5. Suppose we include 40 and 60 as our new members. So first thing to notice, 40 and 60, one is 10 above the mean, one is 10 below the mean. They're equally spaced around the mean. So that means they're not going to change the mean. So the mean of the new set is also 50. Well, right away, that's good. That means that none of the other deviations change. Now let's think about this. 40 and 60 each is a distance of 10 away from the mean. Well, the standard deviation is only 5. So these are much further from the mean. In fact, each one is 2 standard deviations away from the mean. Each one is further from the mean than the standard deviation. So adding bigger deviations than the standard deviation will increase the standard deviation of the list. Now, we're not going to have to actually calculate the new value of the standard deviation. It's just enough to realize that if we add 40 and 60 to this set, we're going to increase the standard deviation because we've added numbers that are further from the mean than the standard deviation. All right, reset. We start out with our set of 20. Now we're going to include 45 and 55. Once again, adding two numbers that are symmetrically spaced, 5 above, 5 below. So this is not going to change the mean. We're going to stick with the same mean, the mean of 50. And now we're adding two numbers that are exactly at the standard deviation on either side. One is one standard deviation above the mean, and the other is one standard deviation below the mean. Each one has a deviation from the mean exactly equal in size to the standard deviation. So that means they're not going to change the standard deviation at all. This new set will have exactly the same standard deviation as the old set. So the old standard deviation and the new standard deviation both equal 5. So this is the only time you'd need to know the new standard deviation, know the numerical value, because it stays the same. It's the same as the old numerical value. All right, reset back to the set of 20. Now suppose we include two numbers that are closer to the mean, say 47 and 53. Well, now we add two numbers, again, symmetrically spaced. One is 3 below the mean, 3 above the mean, so this will not change the mean. The mean will stay the same. And so now, notice that these have a separation of the mean that is less than the standard deviation. They are closer to the mean than the value of the standard deviation. And so that means they would decrease the standard deviation. Now, we don't need to be able to calculate the new standard deviation, but we need to recognize that the standard deviation would decrease if we added these two numbers. Now, we might get curious, what pair of numbers could we include that would most decrease the standard deviation? Well, we'd have to include a pair with the smallest possible distance from the mean. The smallest possible distance from the mean, of course, is 0. You can't have a distance smaller than 0. If the two new members of the set we include are 50 and 50, these two members each have a distance of 0 from the mean, so they decrease the standard deviation the most. Of all possible pairs of new members we can include in a set, including two new members equal to the mean of the set, is the pair that would decrease the standard deviation the most. The test likes to ask about that idea. So here we go. You can see we've added those 2 points right at the mean. They're going to have deviations of 0. And so if you think of the list of deviation, putting 2 more zeros on that list, that decreases the standard deviation. And once again, we don't need to be able to calculate this new standard deviation, but we just need to recognize that it has decreased the most. The second topic concerns the standard deviation as a unit of measurement. Well, what do I mean by this? In very large sets, for example, populations of countries or everyone who takes the SAT, some kind of gigantic set like that, we may want to specify the position of an individual with respect to the population. If we are told that the mean of a certain set is 50 and somebody's score is 60, what exactly does that mean? Yes, that score of 60 is above the mean. Is this just something kind of mildly above the mean, or is this a really, really impressive score far above the mean? Well, think about it this way. If the mean is 50 and the standard deviation is 20, then 60 is above the mean. It's half a standard deviation above the mean, but presumably many numbers are going to be higher than that. It would not be unusual in a set to have numbers that are as far as a standard deviation away from the mean or even further. So we'd certainly expect that there be some numbers that are one standard deviation above the mean, maybe even one and a half standard deviations above the mean. So we'd expect scores of 70 and 80. So 60, yeah, it's above the mean, but it's not among the highest scores. And so it's kind of on the good side of average rather than being a super impressive score in this particular set. Notice what happens if we change the standard deviation, though. By contrast, if the mean is 50 and the standard deviation is 2, then 60 is very, very far above the average. Because it's the standard deviation that tells us how meaningful a certain separation from the mean is, mathematicians generally use the standard deviation of any set as a unit of measurement within that set. If this individual is 10 units above the mean and the standard deviation is 2, then this individual is 5 standard deviations above the mean. Now, it's hard to emphasize how extraordinary that would be, 5 standard deviations above the mean. In terms of musical abilities, that would be the best musician in the world. In terms of athletic abilities, that would be the best athlete in the world. That would be just someone off the charts, like once every 100 years kind of talented. That's how impressive this score would be if it were 5 standard deviations above the mean. Here's a practice problem. Pause the video and then we'll talk about this. On a certain test, the scorer had a mean of 300 and a standard deviation of 25. If John scored 3 standard deviations above the mean, what was John's score? Well, the mean is 300, and he scored 3 25s above 300. Well, that would be 300 plus 75, which is 375. So it turns out a question like this actually involves a very, very simple calculation. You just have to be not intimidated by the question itself. The final topic, very advanced, concerns the actual calculation of standard deviation. The test will not, repeat, not ask you to calculate the standard deviation of the list from scratch. But on a very advanced question, it could ask about some detail, some concept related to the details of this calculation. Here are the steps in the calculation. So first of all, we start with a list of numbers. We have to find the mean. As we said, we subtract the mean, and this creates a second list, the list of deviations. Then we're going to take that list of deviations, some are positive, some are negative, we're going to square that list. So that will be a list of squared deviations, a third list. That list will be all positive numbers because we've squared them. Now we're going to take an average of this third list, the average squared deviation. And that number is actually called the variance. Once we have the variance, we're going to take a square root, and this is the standard deviation. Okay, so now we'll do a sample calculation. We'll start with a very simple list, just the integers from 1 to 9. So this is a nice symmetrical, evenly spaced list. Of course, the number in the middle, 5, that would be both the mean and the median of this list. So we have the mean, so it's easy to figure out the deviations. To get the list of deviations, I'm just going to take list number 1 and subtract 5 from every number on the list. So 5, of course, has a deviation of 0. The numbers less than 5 have negative deviations. The numbers bigger than 5 have positive deviations. That's the second list. Now to get the third list, we just square everything. So those are the squares. Notice 0 squared is 0. Everything else is positive. So now we have the list of the squared deviations. Now we average that third list. The average of that third list is something called the variance. So the variance, the average of that list happens to be 20 over 3. That's the variance, and that is the variance of the first list. The first list has a variance of 20 over 3. To find the standard deviation, we take the square root of the variance. So we could write it in radical form. We could simplify that radical if we wanted to. Typically, the standard deviation is just written as a decimal. So we'll write it in a decimal form. So notice that what we found here, 2.582, this is the standard deviation of the list from 1 to 9. And also, because of what we learned in the last video, this would be the standard deviation of any 9 consecutive integers. So any 9 consecutive integers at all would have a standard deviation of 2.582. That is the entire calculation for standard deviation in all its gory detail. The test will not ask you to repeat that entire procedure. Conceivably, on the very hardest quant problems, it could present some part of that procedure, could ask about some detail. One thing to notice, incidentally, because we're squaring, numbers that are larger, numbers that have larger deviations, make a larger contribution to the standard deviation, a much larger contribution. The effective squaring amplifies the input of the numbers that have larger deviations. That's an important thing to notice. You may wonder why the standard deviation is defined in this particular way. This is related to its principal use. We could find the standard deviation of any list or set, but in some ways the standard deviation is designed to accompany the normal distribution, which we will discuss in the next video. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so let's talk about this problem. The camp has 30 girls whose heights have an average of 130 centimeters and a standard deviation of 4 centimeters. Suppose 4 more girls join the camp, so there'll be 34 altogether. Which set of heights for these 4 additional girls would most increase the standard deviation of all the girls at the camp? Well, certainly if we wanted to least increase the standard deviation, if we wanted to decrease the standard deviation, we'd be adding girls who all had values of 130. They'd all be equal to the mean. Well, we don't have any like that, but notice with C, 2 of them are equal to the mean, and the other 2 are very close to the mean. So all 4 of them are closer to the mean than the standard deviation, so that's going to decrease the mean. So that's certainly not going to increase. If we add the ones in B, notice all 4 of those. We have deviations of -3, -1, 1, and 3. So those are going to all be deviations that, again, are less than the standard deviation. So that's also going to decrease the standard deviation. So that's not going to be right. Very interesting, if we look at A, there we have deviations of -4, -4, 4, and 4. All 4 of those numbers are exactly 1 standard deviation away from the mean. So in fact, adding those 4 girls will keep the standard deviation at exactly 4, because we're just adding more standard deviations, more deviations of the same value. So that's going to stay the same, and so that's not an increase. So the only one that's left is D, and if we look at D, what we're adding there are 4 outliers. Each one of them is 2.5 standard deviations away from the mean. That's far away from the mean. And so that's going to change the mean of the whole camp. It's going to upset all the deviations, and the net result is that you're going to have much larger deviations and a much larger standard deviation. So D is the answer. In summary, we discussed the effect of on the standard deviation of including a new pair of numbers in the set, and notice that we can talk about that most sensibly if we're adding 2 numbers that don't change the mean. We discussed using the standard deviation as a unit to indicate the position of an individual in a large population, talking about how many standard deviations above or below the mean. And we discussed the technical details of the exact calculation for the standard deviation. Now we can talk about the normal distribution. In order to talk about the normal distribution, first we'll talk about histograms. A histogram is a graphical way to display the data in a set. Suppose a set has 30 elements. If we wanted to know where the numbers fell relatively to each other, scanning the list of numbers would take some time. In other words, if we look at a page of numbers, it can be hard to determine, and that's only with 30 numbers. And you can imagine if you had 100 numbers or 1,000 numbers, it would be very hard to scan that list. So instead, a histogram allows us to see the whole distribution at a glance. So the way we read this is, so for example, between 95 and 100, there was 1 person with a score in that range. Between 90 and 95, there were 2 people in that range. So there were 3 scores between 90 and 100. Between 80 and 90, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 scores, and so forth. So each score is represented as a box. We don't have the exact score. In other words, we know that those 7 scores are between 80 and 85. We don't know the exact score, but that's okay. This gives us the overall sense of the distribution. For example, here we can see that the person who had the low score, somewhere between 55 and 60, they were quite far away from everyone else. So it was rare to get that low, and it was rare to get in the 90s on this particular test. The horizontal axis of a histogram is always the quantitative variable in question, the number variable that we're exploring. The vertical axis is always something we call the frequency. That is, how many people or items fall in that particular category. So for example, with the test scores, the horizontal axis was the actual scores on the exam, and the vertical axis, that told us how many people fell into each bucket. And we call that the frequency. How frequent was each bucket inhabited by a particular score. We could do a histogram for 100 individuals or 1,000 or 10,000, and of course, the higher the number, the much easier the histogram is than to deal with the list of numbers. If we had 10,000 numbers, that would be a short book. Rather than flipping through all those numbers, we could just look at a single histogram and right away tell the high points and the low points. And of course, when we make the numbers higher, we'd have to make the bars skinnier. Well, you can imagine where this is going. Instead of 100,000, suppose we had millions or hundreds of millions. Suppose we're dealing with the population the size of an entire country. Well, then what's going to happen essentially, the bars get so skinny that it becomes continuous, and the shape becomes a smooth curve called the distribution of a population. And so in statistics, there are many possible distributions, but for the test, you need to know just one. The most common and most famous distribution in the whole world, the normal distribution. Sometimes it's called the Gaussian. That's the more mathematical term. The common term is just the bell curve. I'll be calling it the normal distribution. And so if we imagine really, really skinny bars, what we have here is we have a lot of people right in the center, and then it drops off sharply, and then we just have some rarities out toward the edges. Now, why is this a famous curve? Well, in measurements of bodily features or innate abilities. So, for example, suppose you went and you surveyed everyone on Earth. What is the length if you have them bend their arm and you measure from the tip of their middle finger to their elbow? Or you measure the distance between their eyeballs. Or you measure the height of their ear. Or any measurement on the body you could possibly make. Or you could measure some kind of psychological ability, their reaction time. An image pops on the screen and they have to click on something. And how fast should they react to that? If you measured that for everybody on Earth, those abilities would always fall into a bell curve. And you could do this for humans, animals, plants, any living things, all biological systems, anything you could possibly measure about a biological system over a whole population, it follows a bell curve. Similarly, it's also common in measurements of populations of mass-produced items. So, for example, a machine is making screws or making any kind of part. Well, of course, each part is not going to be identical. There's going to be some small variance, but it's very typical that the overall variation in all the screws produced by that single machine, that they would vary according to a normal distribution. So you'll see the normal distribution pop up in many word problems. And I just want to assure you, it's not at all something that the test maker is making up. In fact, many things in the world do follow the normal distribution. Now, it's very important to realize all normal distributions have a number of properties in common. These properties become clear if the horizontal axis, instead of measured in the ordinary units, pounds or kilograms or inches or something like that. Instead, if we measure it in standard deviations. In fact, when we measure in standard deviations, all normal distributions look the same. So in the following graphs, I'm just going to use the abbreviation M for the mean and S for the standard deviation. And this is what essentially every normal distribution in the world looks like. So one property is that first standard deviation, from the mean to one standard deviation above the mean, 34% of the population falls there. And of course, the bell curve is completely symmetrical, so it means that in this corresponding region here, there's another 34%. So within one standard deviation, from one side to the other side, 68, that's 34 times 2, 68% of the population is within one standard deviation of the bell curve. And so here we just have it stated. Between the mean and the mean plus one standard deviation is 34% of the bell curve, also between the mean and one mean minus one standard deviation. That's another 34% of the bell curve. Also, that region up there is 13.5%. So this is the region between one standard deviation and two standard deviations. And of course, the corresponding region here would also be 13.5. And from these pieces, you realize you could build all kinds of things. For example, we could ask from the mean to two standard deviations above the mean, how much would that be? Well, that would be 34% plus 13.5, and so that would be 47.5% of the population. All you have to do is memorize those two numbers, 34% and 13.5%, and you can calculate everything else. Of course, the mean equals the median, so 50% are above the mean and 50% are below the mean. That's always true for a normal distribution. How many points are further than two standard deviations above the mean? Well, think about this. In other words, we'd have to take that 50% that's above the mean, subtract the 34% that's between 0 and 1 standard deviation, and then subtract the 13.5% that is between 1 standard deviation and 2 standard deviations, and that will just leave a little bit up in the tail. So 50 minus 34 minus 13.5, and that gives us 2.5. So 2.5% of the population is above 2 standard deviations above the mean. And incidentally, 3 standard deviations above the mean, then you're getting up into people that are 1 out of, say, 1 out of 1,000. You get up to 4 standard deviations, it's something close to 1 out of 10,000. So those are the truly exceptional people, the people that are experts or professionals and just world-renowned in their abilities in one particular field, music, athletics, anything like that. Here we have, incidentally, the little tail region, 2.5% in the tail. That is just 2 standard deviations above the mean. From there, all the way up to infinity. Here's a practice problem. Pause the video and then we'll talk about this. So this is approximately true. For adult males, heights are normally distributed with a mean of 175 centimeters and a standard deviation of 10 centimeters. What percent of adult males have a height less than 185 centimeters? Well, notice that 185 is 175 plus 10. In other words, the mean plus 1 standard deviation. So we want to know how many people are below that point that is 1 standard deviation above the mean. So of course what this is going to be is, first of all, the folks between a mean and 1 standard deviation above the mean, as well as everyone below the mean. So that's going to be the 50% that's below the mean, and the 34% that is between the mean and 1 standard deviation above the mean, and that's going to equal 84%. And we can see it graphically here, everyone below 1 standard deviation above the mean. In summary, histograms visually display data. The heights of the bars represent the frequency, that is, how many people fall into each slot. For population size sets, histograms become smooth distributions. You could just imagine those bars getting skinnier and skinnier until just the overall shape remains. You need to know the normal distribution, the bell curve. You need to know the basic properties of that because it's very common in any natural population or in any kind of population of machined items. And on any normal distribution, 34% of the population is between the mean and 1 standard deviation above the mean, and 13.5 is between 1 standard deviation above the mean and 2 standard deviations above the mean. And if you know those two numbers, 34% and 13.5%, you can ask just about anything the test is going to ask about this. Quartiles and boxplots. First, we need to discuss the issue of quartiles. What exactly are quartiles of a distribution? Imagine putting a list of numbers in order from lowest to highest. Of course, the middle number on that list would be the median. We've already talked about that. The quartiles are three numbers that would divide this list into four smaller lists, four equally sized lists. The first of these numbers, the first quartile, Q1, divides the bottom 25 from the rest of the list. So it marks off the lower quarter from everyone else. That's the first quartile. You might suppose that the second number would be called the second quartile, but think about it. Since this number divides the lower 50% from the upper 50%, it is exactly in the middle of the list. That's the median. The second number in the set is the median. The median is one of the quartiles. Technically, it is the second quartile, but nobody calls it that. The third number is the third quartile, which divides the lower 75% from the upper 25%. These three numbers divide any list into four equal subsets. So from the min to the first quartile is 25%, from the first quartile to the median is 25%, from the median to the third quartile is 25%, and from the third quartile to the maximum is 25%. Now, how do we calculate them? Well, we've already discussed how to find the median. If n is odd, then the median is the middle number on the list. If n is even, then the median is the average of the two middle numbers. In other words, it's not equal to a specific number on the list. Suppose we have a list of numbers and we found the median. The median divides the whole list into two smaller lists, the upper list and the lower list. If the median is a number in the set, it is not included on either of these lists. So imagine where the median is. You might draw a circle around it or mark it off in some way. Everything above the median, that's the upper list. Everything below the median, that's the lower list. Q1 is merely the median of the lower list, and Q3 is the median of the upper list. So that's the convention we're going to be following. Now, I'll mention there are other conventions. There are other software packages that do things differently. Calculators sometimes do it differently. Other textbooks will explain it differently. I am explaining the convention used on the GRE. So you may get confused if you look somewhere else. This is the convention that the GRE follows. In a moment, I will show some numerical examples with a couple small sets. I just want to make this point first. Quartiles exist as tools to make sense of large data sets, ultimately population-sized data sets. For example, we might want to know the quartiles of household income in the United States for every single household in the United States. We're talking about tens of millions, hundreds of millions of points. There's something a little silly about calculating quartiles for a set that has, say, 10 or 12 members, but we do it for pedagogical purposes so you can get a sense of what the quartiles are. So just keep that in mind. What we have here really is a tool for understanding how population size sets operate, but in order to understand how it works, we're going to need to look at a couple tiny sets. So it's a bit hokey what we're doing, but just suspend belief on that point so we can talk about how this works. All right, suppose we have this set, a not very big set, and we need to find the quartiles. Well, the median is the average of the two middle numbers. There are 10 numbers on the list. The fifth and the sixth number are the two median numbers, 9 and 13. We average them, we get a median of 11. All right. So imagine we draw a line between the 9 and the 13. That's where the median would be, and that divides it into an upper list and a lower list. The lower list are the five lowest numbers, 2, 4, 6, 7, 9. The median is clearly in the middle of that list, 6. That's Q1. The upper list, 13, 13, 13, 14, 14. That is the median. The middle is 13. That has to be Q3. Now a totally new set. We're going to find the quartiles again. The median number is 11. This number is excluded from both the upper list and the lower list. So what we have here is a total of 13 numbers. We exclude the 11 in the middle. And then the lower list, those are all the numbers below 11. The median is 4. Technically, it's the average of those two middle 4s. The upper list, the median is 15. Technically, it's an average of those two middle 15s. And so we have Q1 is 4, median is 11, and Q3 is 15. Once again, for a relatively small set, one in which we can see all the numbers at a single glance, the quartiles don't serve much of a purpose. The purpose of quartiles is to make sense of larger sets of numbers. Once again, there are many other ways to define Q1 and Q3, but what I presented here is the convention that the GRE follows. If you look in other sources, they may define it differently and you may be confused on these points. So just keep that in mind. There are other ways to define this. I'm showing you the way it's used on the GRE. Here's a practice question. Pause the video and then we'll talk about this. A set of 1,203 alumni from a set of colleges take the GMAT and each gets a score. And as you may know, the score on the GMAT goes from 200 to 800. If the first quartile of these scores is 510, incidentally a not very impressive GMAT score there, and only one student got exactly that grade, then how many of the students scored higher than that? Well, let's think about this. There are 1,203 alumni in this population. The whole set is odd, so the median is on that list. And so that means if we exclude the median, we put a circle around the median and exclude the median, we'd be left with 2,002 numbers. Divide that number in two, 601. That's each half list. So there's 601 people on the lower list and 601 people on the upper list. Now let's look at the lower list. It's also odd, so the median is on this list. So we remove the median of that lower list, we're left with 600, and then we can divide that easily by 2. That's 300 above, 300 below. So that means that there's 300 below the first quartile and 300 between the first quartile and the median. So let's think about this now. There are 300 below the first quartile. Then there's the single first quartile score. Then there's 300 above the first quartile. Then there's the single median score. And then there's the 601 on the upper list. Well, of these 5 buckets, who is above Q1? Well, of course, these 3. So if we add up the 300 plus the single median plus 601, they add up to 902. 902 scores are exactly above that score. Often the mean, the median, and Q1 and Q3 are cited with the max and the min to give a full sense of the distribution. These 5 numbers are sometimes called the 5-number summary of a distribution. That's a term you don't need to know for the test, but sometimes you'll see those 5 given. And they are often summed up conveniently in a graphical form known as a box plot. So now we're ready to talk about box plots, now that we know what quartiles are. This is the general box plot shape. So there's always this rectangle in the middle with a vertical line somewhere in the middle of that rectangle, and then these 2 kind of arms on each side that consist of just a horizontal line going to an isolated vertical line at each end. Notice that this shape contains 5 vertical segments. So here we have the shape, and I've marked the 5 vertical segments in red. These represent from left to right the minimum, Q1, the median, Q3, and the maximum. So, in other words, the vertical segments show the position of the numbers in the 5-number summary. The box plot is displayed over the numerical scale of a variable to demonstrate the distribution of that variable. So, for example, here we have a box plot. We don't actually know what this is. This might be, for example, the GMAT scores that we were just talking about, because GMAT is something that goes from 200 to 800. So let's just pretend that these are GMAT scores. Here we can approximate that the minimum in the set is 400. Q1 is around 450. The median appears to be right at 500. Q3 appears to be around a little over 600, say 620. And the max is just below 800, so let's say 790. And so that is the 5-number summary of this score of distributions. Here's a question. If the 4 quartiles divide the population into 4 equal parts, why aren't the gaps between the vertical lines always the same size? So what we have here, we see completely different size gaps between the minimum and Q1, between Q1 and the median. Those are relatively small. Q1 and Q3 is very large, and Q3 to the max is the largest. Why are they different sizes if there's 25% of the population in each one? Well, first of all, think about it. There's never any guarantee that the median will be the average of the max and the min. So right there, there's no guarantee. If you know your max, you know your min, there's no guarantee that if you average those two, you'll get the median. The median could be anywhere between the max and the min. More generally, the gaps from one bar to the next represent difference in score, not difference in number of people or points. So from Q1 to Q3, that's a narrow gap because the score, from the minimum to Q1 is a narrow gap because the score difference, from the minimum score to the score at Q1 is a very small difference. 25% of the population is in that very narrow distribution of scores. Meanwhile, at the top of the distribution, from Q3 to the max, is gigantic. That means that the top 25% have scores that are really spread out. So the bottom 25%, in fact, the bottom 50%, all have scores that are very close together, whereas the top 25% are really, really spread out. Here's a practice question. Pause the video and then we'll talk about this. Okay, at a large university, 2,800 students take Biochemistry 101. The box plot shows the percentage grades on the first midterm. What can you say about the mean? Well, here's the thing. We know the median. The median is right here, around 30. The box plot does not directly show the mean, but we can make inferences about it. Notice that we could ask the question, where are the outliers? On the left side, everything is pretty close together on the left side, but on the right side, holy smokes, it seems to go on forever. The outliers are clearly on the right in this distribution. And so, if you remember, comparing mean and median, the mean gets pulled in the direction of outliers. We talked about this way back in the lesson on mean and median. So if the mean is pulled in the direction of outliers, that means that the mean has to be pulled above the median, and therefore the mean is higher than 30. And that is the answer. In summary, the quartiles, Q1, the median, and Q3, divide the whole list into 4 equal lists. Q1 is the median of the lower list, Q3 is the median of the upper list. That's how we calculate it on the GRE. Again, other sources will do it differently, but this is the GRE convention. The max and the min and the 3 quartile numbers constitute the 5-number summary, and these determine the 5 vertical lines on a box plot. And the general shape of a box plot is as follows. We'll talk more about box plots in the next video. So in the last video, we talked about the basics of the box plot. The box plot shows in visual form those 5 important numbers: the minimum, the first quartile, the median, the third quartile, and the maximum. Now we can talk about why the box plot has that particular shape. Of course, the distinctive thing is the box itself, that box right in the middle, the feature that gives this figure its name. Yes, we need to show the positions of the 5 vertical lines. We talked about the importance of those last time, but why are the middle 3 connected by a box? What's up with that? Think about the numbers that make up this box: the first quartile, the mean, and the third quartile. Of course, 25% of the population is below the first quartile, and 25% is above the third quartile. So those are the 2 regions outside of the box. So outside the box, we have 25 on one side, 25 on the other side. So that means the box itself is 50%. And that's 50% of the population between Q1 and Q3. That is the middle 50% of the population. This is what the box on a box plot represents. This can be a confusing idea, so let's take this very slowly. Below the median is the lower 50% of the data, and above the median is the upper 50% of the data, but between the 2 quartiles is the middle 50% of the data. The upper and lower 50% regions are likely to include outliers and extreme values. The lower 50% goes all the way down to the minimum. The upper 50% goes all the way up to the maximum. Well, at the max and the min, those are where you're likely to find outliers and extreme values. The middle 50%, that's the middle 50% closest to the median, to the middle of the list. That's the 50% at the exact middle of the population. So that's a very representative slice of the population that does not include any outliers at all. The size of this region, the size of the middle 50%, given by Q3 minus Q1, is called the interquartile range, or the IQR. So that is the range of the middle 50% of the data. It's also the horizontal length of the box in a box plot. The advantage of this measure of spread is that it reflects the spread of the most typical values, not the extremes. Here's a practice problem. Pause the video and then we'll talk about this. Okay, in the above distribution, the total range of values equals k times the interquartile range. Find k. Well, fortunately, we can read everything here. The minimum appears to be around 15. The max appears to be around 95. So 95 minus 15 is 80. That's the range, max minus min. Now the interquartile range, it looks like the first quartile is around 40. The third quartile is around 60. So the IQR, 60 minus 40, is 20. And so k is how many times we're multiplying 20 to get 80. 20 times k equals 80. So of course, k is 80 divided by 20 equals 4. And what we're really saying is that the whole length of this box plot from left side to right side is about 4 times as long as the length of the box in the middle. Or in other words, the distance from the lowest score to the highest score, that total range is 4 times larger than the spread across the middle 50% of the data. Now notice, in the above population, I was saying 25% of the population is below Q1 and 50% is below the median. I was making these broad percentage statements. These statements are not always true because, for example, in the set, and here we have a set with only a few values, the mean is 5, Q1 is 5, and only one number is below that value. So the percentage statements certainly do not work. Remember that quartiles and box plots are tools designed to make sense of a large population, something the size of a whole country, for example, hundreds of millions of data points. So on that scale, repetition and other irregularities happen across too small a range to matter. So yeah, if we look across the whole population, yeah, there are going to be coincidences where maybe 2 different people have the same income or something like that. But those small repetitions, they're going to be too small to matter in the grand sweep of the whole population. On that scale, the percentage statements about median and the quartiles and the IQR are 100% perfectly accurate. So the box of the box plot is the middle 50% of the population, called the interquartile range. This middle 50%, the IQR, equals Q3 minus Q1. The percent interpretations of median and the quartile works only if the data set is the size of a real population. So in other words, if you're looking at a set that has 10 members or something like that, of course the percentages here are not going to work exactly. They're not supposed to. They're supposed to work at a population level.
Now that we've talked about box plots and the numbers associated with box plots, we can talk about percentiles. Percentiles are one more way of discussing the position of an individual score in a large population. Now you may wonder, since we already have those numbers associated with box plots, why do we need something else? Why do we need percentiles in addition to box plots? Well, percentiles are more precise than the box plot numbers. For example, think about GRE math scores. On the GRE math section, a score of 160 is between the third quartile and the max. A score of 167 is between the third quartile and the max. Well, saying it like that makes it sound like those two scores are equivalent, as if they're more or less interchangeable. And of course, that's not the case at all. When we talk about percentiles, the difference becomes clear. A score of 160 is the 78th percentile. A score of 167 is the 95th percentile. Well, holy smokes, that's a big difference. Let's talk about what that means. So let's back up. First of all, in the abstract, if a score is in the 40th percentile in a large distribution, this means the score is larger than 40% of the distribution. It is larger than 40% of the scores. And in general, that pattern holds. I'll state it in terms of a variable. If a score is the pth percentile of a distribution, that score is larger than p% of the scores in the distribution. And of course, p could be anything between 1 and 100. Let's go back to those GRE scores and look at them again. A score of 160 on the GRE math section is the 78th percentile. So what that means is if you score 160 on your GRE math, you have scored higher than 78% of GRE takers on the math section. So 78%, that is slightly bigger than 75, so you've done better than slightly more than 3/4 of the people who take the GRE. Not bad, but consider 167. 167 is the 95th percentile. If you get 167 as your GRE math score, that means you've done better than 95% of the people who take the GRE. Or another way to say that is you have a math score that is in the top 5%. Now that's very special, and that is much more impressive than the 160. And percentiles is what allows us to talk about this subtle but important difference. Now, a few things to keep in mind about this. First of all, percentiles only make sense for large distributions. Everyone taking the GRE, everyone with a driver's license in the state of California, every household in the nation of Japan, something like that, a gigantic population. It doesn't make sense to talk about percentiles when you have a list of 5 or 10, something like that. It just doesn't make sense to use it for short lists. It is only used for populations. Notice that the percentile of the minimum score, the lowest score, is the 0th percentile. So let's think about this. Suppose there's a test, and suppose I get the absolute lowest score on that test. Well, if I get that score, it means that my score is higher than 0% of the population, and therefore I would be the 0th percentile. So that's more or less straightforward. The lowest score is the 0th percentile. Here's the one that's tricky, though. The percentile of the highest score is the 99th percentile. In other words, there's no such thing as a 100th percentile. Now, why would this be? Suppose I get the highest score on the test. Well, to be the 100th percentile, I would have to have a score that is higher than 100% of the scores. And the problem with that is my own score is one of the scores, so to be the 100th percentile, I'd have to get a score that was higher than my own score. And of course, that's impossible. So the highest you can get in whole numbers is the 99th percentile. Now sometimes people get into very fine distinctions. We can talk about the 99.9 percentile, the 99.99 percentile, something along those lines, but the 100th percentile is impossible. Keep in mind there's a very close correlation between the numbers that we just talked about in box plots and percentiles. Of course, the minimum we just said is the 0th percentile, the maximum is the 99th percentile, and approximately the first quartile is the 25th percentile, the median is the 50th percentile, and the third quartile the 75th percentile. And I say approximately, if we're only talking about 1,000 or a couple thousand people, these numbers are going to be approximate. They'll be much more accurate the larger the population is. By the time you're talking about a population that is the size of an entire nation, these equations here will be exact. Keep in mind also, we can talk about how this fits in with the normal distribution, which you talked about a few videos ago. So these are the actual numbers that you saw in the normal distribution video. Well, let's think about this. The center number, of course, is the mean, the median, and the mode. So that number right in the middle, the mean, that is the 50th percentile. Well, if we go one standard deviation below the mean, so drop down 34%, that means that this number here must be the 16th percentile. You're there, you're higher than 16% of the population. If we go up a standard deviation above the mean, then we add 34%, and so that means here we're at the 84th percentile. And if we go another standard deviation above the mean, we add 13.5, that puts us at the 97.5 percentile. And so if you are 2 standard deviations above the mean, you are scoring higher than 97.5% of the population. Incidentally, if you are 3 standard deviations above the mean, you are well above the 99th percentile. And so that is how percentiles work on the normal distribution. Finally, this is a very subtle and difficult idea to understand. Halfway between percentiles is not the same as halfway between scores. What do I mean by that? Well, consider this theoretical practice question. If 660 is the 70th percentile of a normal distribution, some kind of normal distribution, and 760 is the 80th percentile, then what can we say about the 75th percentile? So this is kind of a vaguely worded question. This might be worded much more precisely, for example, as a quantitative comparison. But the basic idea is we have a normal distribution. And we're up on the upper arm of the normal distribution. So we're at the part of the normal distribution where it's descending like this. And somewhere here is 660, and that's the 70th percentile. And somewhere here is 760, and this is the 80th percentile. So we know that between here, this is all 10% of the population. And we want to know, if we go right in the middle, how does that number right in the middle compare to the 75th percentile? Now, the mistake would be to think that the percentile that's in the middle is exactly the same place as the score that's in the middle. And problems like this, people fall into that trap all the time. But let's think about this very carefully. Where are there more people? Toward this side or toward this side? Well, we can see the normal distribution is sloping down here. And so we can see there's many more people on this side and many fewer people on this side. And in fact, if we just think of the area of this whole thing, where would we draw a vertical line to cut this area in half? And I'm going to guess it would be around here, approximately. In other words, I'm going to say that this area here is approximately equal to this area here. We have this sort of short, chunkier area, and then this long, thin area, and they're about the same. And so notice that the place where we put the line that cuts the area in half, that would actually be the 75th percentile. So 5% would be on one side and 5% would be on the other side. And notice that this is lower than the score right between them. So the score right between them would be 710, exactly between 660 and 760. And so the 75th percentile has to be lower than 710. So again, this is a very subtle problem, but this could come up on some of the more difficult math questions on the GRE.